अब दिख रहा है? हेलो।
यस सर।
हाँ, अगर कहीं प्रॉब्लम आती है तुरंत बता दिया करो, अदरवाइज मैं आगे निकल जाऊंगा, फिर तुम लोग को समझ में नहीं आएगा। ठीक है। सो नेट रेट ऑफ इनफ्लो ऑफ मोमेंटम बाय विस्कस ट्रांसपोर्ट, विस्कस मींस ड्यू टू द फ्रिक्शन। ओके, सो मोमेंटम may be transported due to the flow of the fluid. Momentum will be transported, may be transported by the viscous forces. Okay, plus summation of all forces. So what are the other forces? Pressure force and gravity force. The major force which will include in the equation of motion is the pressure force and the gravity force. We will not include the centrifugal force in the equation of motion because centrifugal is generally not considered in the different operations. There are some operations where the centrifugal force is important, and when it will important, you can modify the equation. Okay, but the major in the majority of time there is a no centrifugal force, then you have to add the pressure force and the force due to the gravity. ठीक है। now what we will do, we will use the similar
एक्सक्यूज मी
approach.
सर।
हाँ बोलो।
सर आप जो लिख रहे हैं वो दिख नहीं रहा है, मतलब आप लिखता हुआ नहीं दिख रहा है, वो फ्रीज हो गया फिर से। हाँ सर अब दिखा। मतलब सर जब आप लिखते हो तो नहीं दिखाई देता है।
आई थिंक कुछ प्रॉब्लम है आज। मैं एक काम करता हूँ, मैं इंटरनेट कनेक्शन चेंज करता हूँ, उसके बाद चेक करते हैं, है ना, एक मिनट रुको। कुछ तो प्रॉब्लम है, एक बार स्टार्ट करते हैं फिर से, है ना? अब एक बार चेक करना, एम आई ऑडिबल?
यस सर।
यस सर।
दिख रहा है अभी? स्क्रीन आ रही है
हाँ यस सर,
Yes,
दिख
sir.
रहा है।
ना? So rate of accumulation of momentum in a control volume should be equal to net rate of inflow of momentum by convection. Convection means due to flow of the material. Net rate of inflow of momentum by viscous transport. Viscous transport means the friction forces in the fluid, then pressure force and the force due to gravity. Okay, so all these four, we have to write all these forces, and then we will see how we will derive the equation of motion. Okay, so we will use the similar approach which we have used in the for the equation of continuity, for derivation of the equation of continuity, that we will take a fixed control volume in the space, है ना? A regular shape fixed control volume in the space. We do the momentum balance for that control volume, then we will collapse the control volume to a point. And when we collapse the control volume to a point, the equation will be true for the all conditions. Okay, so we will take a fixed control volume, fixed rectangular control volume in the space. So दिख रहा है लिखते हुए?
नो सर।
अभी नहीं
नहीं,
आया?
नेक्स्ट
अभी
पेज
नहीं
नहीं
आया।
हो रहा है।
अब आया?
हाँ अब आ गया सर, कंसीडर है।
क्या दिक्कत है? मैं पूरा स्क्रीन शेयर करता हूँ, शायद तब ज्यादा अच्छे से आए। दिख रहा है?
यस सर, दिख रहा है।
अब बताओ,
हाँ लिख,
आ रहा है
कंसीडर
लिखते हुए? कंट्रोल वॉल्यूम,
यस सर, अब दिख रहा।
हाँ। So consider a control volume having volume delta x, delta y, delta z fixed in space. That means control volume is not moving in a with time, that is fixed in the space. There are other approaches also to derive these equations. In that approaches, we will take the in regular shape control volume, and that is flowing with the flow rate. But that in that approach, the mathematics required to derive the equation that are very complicated. Basically, you have to use the volume integral, volume vector integral, and so that is very difficult to solve. In this approach, we will simply derive the differential equations, and that is simpler approach. Okay, in some books like in Jinkoblish book, which I have already shared with you, and in Jinkoblish book, you will find the volume approach. So what is the volume approach? In volume approach, you will take the in regular shape control volume, which volume is dv, and it is flowing with the velocity v in the space. And then you have to do the force balance, momentum balance for this control volume. And so that is one approach. In that approach, you have to use the volume integral for the vector quantities, and that is somehow difficult to solve. And in the approach which we are considering, in this approach, we will simply use the vector calculus, differential calculus, where for solving the for deriving the equations. So here we are considering the control volume which has the regular shape. Okay, so this is the rectangular control volume which has the rectangular shape. दिख रहा है?
यस सर।
यस सर, दिख रहा है।
हाँ, ओके। सो दिस इज अ रेक्टेंगुलर कंट्रोल वॉल्यूम। इसको थोड़ा सा और अच्छे से बनाते हैं। So we put the coordinate system because this is the rectangular control volume. We have to use the Cartesian coordinate system, which is easiest control coordinate system to use. Okay, this length, this is the x-axis, so this is the delta x. This is y-axis, so this is delta y, and this is z-axis, so this is delta z. Okay, now what we will do? We will do the momentum balance. Now momentum is momentum is force per multiplied by weight, so it is a vector quantity. So momentum has the three components. Okay, so for each component you can do the separate balance. This is delta y, not delta z. This is delta y. So for each component you can do the separate balance. Okay, so when you use the, like, it is like, suppose you are adding the two vector quantities v plus w. So basically you have to add the vi plus wi del I plus vj plus wj del j plus vk plus wk del k. This you have studied before. When you add the vector quantities, each component should be added separately. So what we will do, we will do the momentum balance for one quantity, and then we will extend that equation for the other components also. Okay, so first we will do the x directional momentum balance. So momentum balance in x direction. Okay, so first term is the accumulation term. So first we will give the numbers to this term. Okay, so this is number 1, this is number 2, this is number 3, this is number 4 pressure forces, and this is number 5. Okay, so we will derive each term separately. Okay, so first we will write the mathematical expression for number 1, which is the rate of accumulation of x directed momentum in the control volume. Rate of accumulation of x directed control volume, x directed momentum in the control volume. So x directed momentum in the control volume, that will be equal to, because it is rate of change of momentum, so it will come del by del t. That only makes it the rate of change with time, multiply by momentum. Momentum equal to density multiply by volume, delta x, delta y, delta z. This is the volume of the control volume, this cube, rectangular cube, multiply by velocity. That will become the momentum. So this is the rate of change of momentum in the x directed momentum in the control volume. So this is equation number 1. Now the second term is net rate of inflow of momentum by convection. So we will write net rate of inflow of momentum, x directed momentum, because we are doing the x directional, है ना? X directed momentum in control volume. Okay, now you have to understand one thing when we are saying the x directed momentum. So x directed momentum may enter from the any direction. Okay, so x directed momentum may enter from the x direction, from the x directed surface. X directed momentum may enter from the y directed surface, and x directed momentum may enter from the z directed surface. So this is the x directed surface. This is the x directed surface. The area of the x directed surface is delta y delta z. Okay, how the direction of the surface is defined? The direction of the surface is defined by the direction of, here I am written this, so you will remember, है ना? Direction of the surface is defined by outer normal. Okay, suppose this is a surface, so this is the outer normal, so this is the direction of the this surface. Okay, so when you see the control volume, delta y delta z, this area, the outer normal is in the x direction, so this is the x directed surface. Delta x delta z, the outer normal of this curve is y direction, so it is the y directed surface. Then the delta x delta y, this surface, the outer normal is in the z direction, so this is the z direction surface. Okay, so you already have the three directional surface here. So you can say x directed momentum may enter in control volume, in the control volume from any surface, from any directed surface. Okay, so what we have to do, we have to write the equation separately for each surface. Okay, so we can say this is, we can represent by A, and now the net rate of inflow of x directed momentum now the net rate of inflow of x directed momentum into CV into control volume into control volume from or the entering from x face, x surface. Okay, so the x directed momentum which is entering or leaving from x surface, that can be written as density. Density is the scalar quantity, it does not have any direction, multiplied by Vx multiplied by delta z delta y, because it is the x directed momentum. So the surface area of the x directed surface is delta y delta z. Delta z delta y, or multiply by, this is the area, multiply by Vx. Okay. So this is the, at x equal to x, this is the momentum entering from the x directed surface minus rho Vx delta z delta y, or delta y delta z Vx at x equal to x plus delta x. So this is the momentum leaving from the control volume. So this is the input minus output from the x directed momentum which is entering and leaving from the x directed surface. Okay. From x directed surface. Now similarly you can write B. So this is equation number 2. Now net rate of inflow of x directed momentum into control volume from y directed surface, from y directed surface. Okay, so similarly it is the net rate of inflow of the x directed momentum from the y directed surface. It will become first rho multiplied by Vy, because it's the y directed surface, multiplied by surface area. So surface area will be the y directed surface delta x delta z. This is the surface area of the y directed surface, multiply, because it is the x directed momentum. So this is multiplied by Vx. So this is the momentum transport, x directed momentum transport from the y directed surface. So it will enters from the y equal to y, and it will leave from the y equal to y plus delta y. So the same quantity minus Vy delta x delta y, delta x delta z, Vx, because this is the x directed momentum, at y equal to y plus delta y. So this is equation number 3. Similarly, you can write the for the z directed x directed momentum which is moving in the z directed from the z directed surface. So the net rate of inflow of x directed momentum into CV, control volume, from z directed surface. So that will be equal to, first you have to write rho multiply by direction velocity in the direction of the surface Vz, multiply the surface area of the z directed surface, that is the delta x delta y, multiply by multiplied by velocity in the x direction, because it is a x directed momentum. That is from z equal to z, it is the momentum entering in the control volume minus the same quantity at z equal to z delta z, that is the momentum leaving from the control volume. Delta x delta y dx at z equal to z plus delta z. Okay, so this is equation number 4. This is equation number 3. This is equation number 4. Okay, so we have written the convective momentum. Okay, now comes to the third point, that is the viscous forces or viscous transport. Okay, so this is the second point is complete. Now the third point, momentum transport, x directed momentum transport due to the viscous transport. Viscous forces. X directed viscous momentum transport. Okay, so the viscous forces can be represented by the shear stresses. Okay, so shear stresses, the shear stress is a tensor quantity. It has the 9 component. So I have already taught you in the transport phenomena class that shear stress is a second order tensor quantity. It has the 9 component: tau xx, tau xy, tau xz. Then tau yx, tau yy, tau yz. Then tau zx, tau zy, and tau zz. This is the component. These are the components of shear stress. Okay. So in all these components, the first indices, है ना? So we can say in the shear stress component, the second indices show the direction of momentum flux, and first indices shows the direction where momentum is flowing. Okay. So I will return this in all shear stress component. The second indices this derivation is quite lengthy, है ना? तो बोर मत होना, बहुत lengthy derivation है इसका. Generally completed in the 3 hours. Okay, the second indices shows the direction of momentum flux. Okay, and first index shows the direction in which the momentum is flowing. Okay, so x directed momentum flowing in the x direction, x directed momentum flowing in the y direction, x directed momentum flowing in the z direction. So direction of flowing means from which surface it is entering and leaving, that is the direction of flow. Okay, so x directed momentum may flow from the x directed plane, x directed momentum may flow from the y directed plane, and x directed momentum may flow from the z directed plane. Okay, so similar to the convective transport, here again you have the three different equations. Okay, and in the second indices shows the direction of momentum flux, and first indices, first index shows the direction in which the momentum is flowing. Okay, so for example, if you have the tau yx, so tau yx is the x directed momentum flowing in the y direction. So tau yx is the x directed momentum flowing in y direction. So you have the three different equation again. Okay, so first is, again we can write ABC. First is, this is the third point. So in the third point ABC, first is the net rate of inflow of x directed momentum by viscous transport from the x directed surface. Net rate of inflow of x directed momentum by viscous transport. So basically we are talking about the viscous momentum. That's why we are writing the viscous transport. By viscous transport in or from x directed surfaces so that can be easily written as, because we are writing the per unit mass. Okay, so we can write tau xx, this is the x directed momentum flowing in the x direction, multiplied by delta z, the surface area, delta z delta y, this is the x directed momentum from which is entering from the x surface, minus tau xx delta z delta y coming from the leaving from the control volume at x equal to x plus delta x. Okay, so it is entering from x equal to x and leaving from x equal to delta x. So this is the equation number 5. Now similarly, you have the x directed momentum flowing in the y direction and x directed momentum flowing in the z direction. Okay, so net rate of inflow of momentum of x directed momentum by viscous transport from y-directed surface so that will be equal to tau yx. This is the momentum which is accelerated momentum which is flowing from the y direction surface, multiply the surface area delta x delta z. This is the surface area of y directed surface, and that will enter from the y equal to y, and the same quantity will leave from the same this is not the same quantity, this is the different quantity because the variables are same. So we use the same notations for the variables. Delta y delta x del x del z at y equal to y plus delta y. Okay, so this is equation number 6. Similarly, you have the equation number 7 when the net rate of inflow of x directed momentum by viscous transport from the z directed surface. This is C. Net rate of inflow of x directed momentum from z surface from the z directed surface. So that will be equal to rho multiply by not rho tau the first indices represent the direction of flow, that is z, and second indices represent the direction of momentum, so that is x. Tau z x multiplied by surface area of the z directed surface, that is the delta x delta y. So it will enter from the z equal to z, and it will leave from the z equal to z plus delta z. Zx delta x delta y, that will leave from z equal to z plus delta z. This is equation number 7. Okay, so we have written the convective transport. These are the convective. This is the accumulation. First the accumulation term, then the convective transport term, and then the viscous transport term, and for the x directed momentum. Now the two terms are remaining, one for the pressure forces and second for the gravity force. So pressure is a surface force, it will again work in the surface direction. So because pressure is a force, so it has only the, it will x directed surface pressure force will work in the x direction only. So pressure is a force, it has the 3 components. So one component is in the x direction, one component in the y direction, one component in the z direction. Okay, so because we are doing the x directed momentum balance, so you have the only the single pressure force in the x direction. Why? Because pressure will always work in the normal direction. Okay, so it is a in normal outward direction. So pressure will work in the normal outward direction. It is a compressive force, and the pressure is a compressive force. So whenever you have the surface, it will work in the normal outward direction of that surface. Okay, so you have the net pressure force in the x direction, that is the point 4. Net pressure force in the x direction, that is the point 4. Net pressure force. 4 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 in x direction. Net pressure force in x direction. So that will be equal to P multiplied by the surface area. Surface area of the x-directed surface is delta y delta z. Pressure is a scalar quantity for so it is not px py pz. है ना? Pressure is a scalar quantity multiplied by the surface area. So it will become the pressure force. Okay. Pressure force at x equal to x minus P delta y delta z x plus delta x. And x equal to x plus delta x. This is x equal to x. So why you have the two quantities? Because we return the pressure is added. Because in x direction you have the two surfaces. Okay. So these two surfaces are in the x direction. This is the x directed surface. This is the behind of this surface. Okay. So basically you have this type of two surfaces which are the x directed surface. Okay, so this is the x equal to x and this is x equal to x plus delta x. Okay, so how the pressure force will work? In x equal to x, it will work in this direction. At x equal to x plus delta x, it will work in this direction. Okay, so pressure force basically is a compressive force. It will compress the body. Okay, so at x equal to x, the direction of force is similar to the direction of the axis. So it is a positive force. So you will get the positive direction. At x equal to x plus delta x, the direction of the surface, that the direction of the force is the opposite direction of the axis. You know, this is the axis. So it is a negative force. Okay. So at the one point it is a positive and the other point it is a negative force. That's why you have the two different points. And here it is not the net. It is not the net flow. And it is not input minus output. Both are forces, both are adding, but the direction of forces are opposite. That's why you have the resultant force. Okay. Now, fifth is the gravity force. So gravity is the volume force. So if you have only the one component for gravity, it will work and on the body. So gravity force in the x direction. So this is equation number 8. Now gravity force in x direction. So basically for x direction, you have to take the x component of the gravity coefficient. Okay, so rho multiplied by delta x, rho is the density. You have to write the mass. So density multiplied by volume, delta x, delta y, delta z, multiplied by the x component of the gravity coefficient, gx. This is the gravity force in the x direction. This is this is equation number 9. Okay, now you have the 9 equations. Okay, starting from this equation number 1, equation number 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I am not writing the all equation in a page because it is not possible. These are the very the big equations. So I am directly going to the next step. Okay, so adding or substitution, not adding. है ना? You can write substituting equations 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you have the 9 equations, equations 1, 2, 3, 4, 5, 6, 7, 8, 9 in momentum balance equation. So momentum balance equation is the statement which we have written first. So this is the momentum balance expression, है ना? Statement. So we have to substitute these values in the momentum balance statement in their appropriate place. This is the first step. Then the second step, which is I am also skipping, then dividing by this equation by volume of control volume. So this is the same step which we have done in the during the derivation of equation of continuity. And first you have to write all components. You have to put in the components in the original statement. Then you have to divide by the volume of the control volume by volume of control volume. So it will become a point. Next step, and taking the limit limits, delta x tends to 0, delta y tends to 0, and delta z tends to 0. Okay, so these are the 3 steps which I am skipping right now because these are very obvious steps. Basically, what you have to do in all equation, because delta x, delta y, delta z are the constant, because initially we have taken that consider a control volume having the volume delta x, delta y, and delta z fixed in the space. So the volume is not changing and the volume of the control volume is fixed. This is a regular shape control volume. So delta x is a constant, delta y is a constant, delta z is a constant. So now in all the terms, you can easily divide the delta x, delta y, delta z. So here delta x, delta y, delta z will be gone in this equation. What will happen in this second equation? Second equation, you will get delta y, delta z will be gone from the both terms. You will get delta y, the rho vx divided by minus at x equal to x minus rho vx at x equal to x plus delta x divided by delta x. Okay, one thing I can do, I can write this second step. Okay, so you can understand what terms you will get. Okay, so this limit I will take later. So I am just doing the 2 step and putting the values and then dividing by the volume of the control volume. Okay, so what terms you will get, that I am writing here. Okay, so first term is the accumulation term. So in accumulation term, when you remove the volume, it will become del rho vx divided by del t. This is the right hand side of the equation. That should be equal to, now come to the equation number second. So the equation number second is this term. So it will become rho vx multiply by vx at x equal to x minus rho vx multiply by vx at x equal to x plus delta x. Divide by delta x. ठीक है? Similarly, you can write the second term plus the second term will be in the y direction. Equation number 3, it will come rho vx rho vy vx at y equal to y minus rho Vy Vx at y equal to y plus delta y divided by delta y, plus the third term, that is rho Vz Vx at z equal to z minus rho Vz Vx at z equal to z plus delta z divided by delta z. Okay, plus now the tau terms will become, so here it will come tau xx at x equal to x minus tau xx at x equal to x plus delta x divided by delta x plus tau, the second term will be the equation number 6. So tau yx at y equal to y minus tau yx at y equal to y plus delta y divided by delta y plus tau zx at z equal to z minus tau zx at z equal to z plus delta z divided by delta z. So these all three are the terms, shear stress terms. Now the pressure force. So the pressure force will come, the equation number 8, when you divide the equation number 8 to the volume of the control volume, it will become plus P pressure at x equal to x minus P at x equal to x plus delta x divided by delta x. This is the pressure, plus the last term, equation number 9, gravity. When you divide the equation number 9 to the gravity, you will get rho gx. So this is equation number 10. Okay, so this is the very big equation, and this is only the x directed momentum. We have not written the y directed momentum and z directed momentum. This is the equation for only the x directed momentum. Okay, now what we will do, we will divide the equation number 10. We will take the limits x tends to 0, y tends to 0, and z tends to 0 in this equation. So these terms will convert in the derivative. Okay, now in equation number 10, take limit that is delta x tends to 0, delta y tends to 0, and delta z tends to 0. Okay, so when you take the limit, it will convert in the derivative form. Okay, so first term will be remain same, because in the first term there is no delta x, delta y, delta z, so that will remain same, rho Vx divided by del t. This is remain same. The second term, it will converted in the derivative, so this will become del rho Vx divided by del x. The third term, that will convert in the rho Vx Vy, or Vy Vx, not Vx Vy, Vy Vx rho Vy Vx divided by del y, the fourth term, first, second, third, fourth term, rho vz vx divided by del z.
सर ये वाली टर्म्स नेगेटिव होंगी ना?
हाँ, these are negative terms, है ना, because that is the, so what we are, I am doing, I am putting it in the bracket. Okay, so these all terms are negative. Next terms are also negative. Okay, so the next term will be del tau xx divided by del x plus del tau yx divided by del y plus del tau zx divided by del z. Okay, now the third term, which is also negative, that is the pressure term, that is del p by del x. And fourth term is rho gx. So basically this is equation number 11. This only represent the x directed momentum balance. So this equation represent the x directed momentum balance. Now similarly we can write the y directed and z directed. So the equations are similar, so I'm directly writing the equation. Okay, so similar equation you will get, you need not to do the derivation again. If you do for the y direction, you will get y directed momentum balance. First we will write the y directed momentum balance. So that is del rho Vy divided by del T. Same equation, just the indices will change. Minus del rho, now instead of here it will come Vx Vy divided by del x plus del rho Vy divided by del y plus del rho del rho Vz Vy. First indices will represent the direction of surface. Okay, so it will represent the Vz Vy divided by del y del z minus the viscous forces, that is del tau xy divided by del x plus del tau yy divided by del y plus del tau zy divided by del z. Then the pressure force minus del p by del z, this is the pressure force in the z direction, plus gravity force, that is rho gy in the y direction. Now similarly you can write, this is equation number 12. Now similarly you can write z directed momentum balance. That is del rho Vz divided by del T equal to minus, this is equal to del rho Vx Vz divided by del x plus del rho Vy Vz divided by del y plus del rho Vz Vz divided by del z minus viscous forces del tau. Now xz divided by del x plus del tau yz divided by del y plus del tau zz divided by del z. Okay, because all equations are similar, so you can directly write without derive it. Now this is not z, this is y here, and here it will z. Del p by del z plus rho g z. This is equation number 30. Okay, so these are the x directed momentum. Equation 11 represent the x directed momentum, equation 12 represent the y directed momentum, equation 13 represent the z directed momentum in the Cartesian coordinate system. And similarly you can derive the equations. If you use the cylindrical control volume, you can derive the equation in the cylindrical coordinate system. If you take the spherical coordinate control volume, you can derive the equation from the spherical spherical coordinate system. Okay, now what we can do based on this equation, we can write this equation in the vector and tensor form. When we write the equation in the vector and tensor form, the equation will be true, or the will be can be used for the any coordinate system. You have to just use the coordinate transformation rule, and you can you can change the equation very easily. Okay, so what I am doing, I am going to write the equation in the vector and tensor form. Okay, now writing above equation, writing the equation number 11, 12 and 13 in the vector and tensor form. Okay, so first term is del rho Vy. So Vy represent the, basically V velocity is the velocity is a vector quantity. So I can write rho is the scalar quantity, del rho V by del T, that is equal to, now the second term here it is del x, del y, del z. This is the delta. Delta is a vector quantity. So you can write equal to minus del dot rho V. Okay, minus again del, because here you have the shear stress terms. So this is also, when you write in momentum, momentum is a vector quantity, not the second order tensor quantity. This is the vector quantity, this is a second order tensor quantity. So you are taking the dot product between the vector and tensor quantity. Okay, so it will become del dot tau. This is the vector quantity, first order tensor. This is a second order tensor. You are taking the dot product, so it will become the first order vector quantity. Minus again pressure forces. So pressure is a scalar quantity, so you need not to. This is the gradient of the, basically gradient of the scalar field, del P. That's why you have studied the vector and tensors in the transport phenomena. Plus rho g. G is the vector quantity. So this is the conversion of equation in the vector and tensor form. You can see that in the original equation you have the 3, 3, 6, 7, 8, 9. Nine components in that in each equation, and you have the 3 equations. So in total you have the 27 different components of the equation of motion. Yeah, this is basically the equation of motion. Now here you can write the same equation in the more simpler form. And you write the equation when you have the only five components, and instead of the 9 components. Now we will again simplify this equation. So how we will simplify this equation, that I will tell you. And now, so this is equation number 14. Okay, now just rearrange this equation. So it will become del rho v by del t plus del dot rho v that should be equal to minus del dot tau minus del p plus rho g. Okay, so this is again the same equation. Now what we will do, we will use the product rules of the derivative. And what is the product rule? You all know how to change the product rule. Okay, so I am applying the product rule in for the derivatives. So when you use the product rule in the first and second components, okay, so the first component, when you use the product rule, the same equation, this is equation number 14, just this equation can be written as rho del v by del t plus v del rho by del t. Okay, so for the first step I have used the product rule, and for the del operations also you can use the product rule. When you use the product rule for del operation, you can write rho v, because dot product always happen between the nearest vector. You know, that I have already told you. When you have the delta I dot delta j delta k, so dot product will comes between the delta I and delta j only, and the nearest vector. Okay, so that's why you have to take the dot product always between the nearest vectors. So when you are taking the dot product in this case, so it will come first, it will come between these two quantities. This is a vector quantity, the second order tensor quantity, this is the vector quantity, so it will come between these two quantities first. So dot del v, okay, plus v. Now it will come again. We will first the del operation, del operate on v. Now del operate on rho v. So it will goes like this, del dot rho v. But the dot product will happen only between these two quantities, and this quantity and this quantity. Okay, because the del will always operate in the dot product will always operate in the nearest vector. Okay, so this should be equal to minus del dot tau minus del p plus rho g. Okay, this is equation number 15. Now I'm just rearranging the equation number 15 again. Okay, when you rearrange the equation number 15 and taking some component common. Okay, so this equation can again written when we can take rho common from the two different parts, two different components. It will become del rho v divided by del t plus v dot del v, because rho is a scalar quantity, it can come outside. These all are the vector quantities. Okay, plus you can take v common here, and the equation will become del rho divided by del t plus del dot rho v. Okay, and that should be equal to minus del dot tau minus del p. This side, left hand side, will remain the same. Okay, rho g. This is equation number 16. Now you can see observe something in this equation. Something goes to 0 because from the equation of continuity, what is the vector representation of the equation of continuity? What is the vector representation of equation of continuity? This term is the equation of continuity. Now from equation of continuity, you can see del rho by del t plus del dot rho v, that is equal to 0. This is the equation of continuity basically. Okay, so this term will 0. So when this term will be 0, then you will get only these terms. Okay, so the equation will become then rho in bracket del v divided by del t plus v dot del v. The second step will be 0. That should be equal to minus del dot tau minus del p plus rho g. So this is equation number 17, and this is the equation of motion. Okay, so this is basically the equation of motion in the vector tensor form. During the derivation of this equation, we have not taken any assumption. You can see that from the beginning of the derivation, we have not taken any assumption. We have not taken time is steady state. We have not taken that the isothermal condition. We have not taken the Newtonian fluid. And we have not taken any one equation, any one assumption. So this equation is true. This is the most generalized equation. This is like the second law of the second Newton's law, and this is the most generalized equation. This is true for the all condition, and for every condition. Whenever you whenever you do use the simple Newtonian physics, this equation will be true, and of course this equation will not true when you are solving some black hole theory, or you are working on the higher dimensions, and or you are working on the quantum theory, then this equation is not true. But otherwise, if you are simply solving any engineering problem, this equation will be true. And whenever you use the Newton's law, Newtonian physics, this equation will be true. Okay. So most of the problems related to the fluid mechanics is solved by using this equation. You have used the initial stage in the transport phenomena where you have done the shell momentum balance, but shell momentum balance is not useful for several difficult problems. Suppose you are solving problem for some a typical type of geometry, the shape of the system is very complicated, then you cannot do the control volume balance because you don't know where the how to make a control volume for this type of difficult complicated geometries. Okay, then you can directly use the equation of motion, and the equation of motion is the very unique equation. This equation again can be written in the terms of substantial derivative. What is the definition of substantial derivative? So what is the definition of the substantial derivative? Substantial derivative means when the variation is occur with the flow of the fluid. And when you are measuring the variation by moving with the flow, that is the substantial derivative. So if A, not A, I will use some other notations, which is most. S is the most common notation. If S is a property, then substantial derivative is defined as del S by del T plus del S by del T plus V dot del S. This is the substantial derivative. This is equal to ds by dt. So basically, this quantity represent that you are measuring the variation with respect to time as well as with respect to space. So, and in the space you are moving with the velocity of the fluid. So whatever is the fluid which is flowing, you are measuring the velocity. You are also moving at the velocity of that fluid. Okay, so this is the substantial derivative. So from this definition, equation number 17 can be written as, because here the property is velocity. You can see the same quantity. Here it is only the velocity. So basically you are measuring the velocity with respect to time and with respect to space. From this definition, equation number 17 can be written as d rho multiplied by del v divided by del t, d capital del v by del t, that should be equal to, the other terms will be same, minus del dot tau minus del t plus rho g. So this is again the another form of equation of motion. Okay, so these are two form of the equation of motion. Okay, now we will continue the derivation. अभी complete नहीं हुआ, there is a derivation बचा हुआ है. So in the next class we will complete this derivation. ठीक है?
ओके सर.
समझ में आया डेरिवेशन तुम लोगों को? एक दो बार पढ़ोगे तो आ जाएगा. दिस इज एक्चुअली वेरी लेंथी डेरिवेशन, बट ऐसा मुश्किल नहीं है इसको समझना. है ना, बेसिकली दे आर डूइंग द मोमेंटम बैलेंस फॉर मोस्ट जनरलाइज्ड केस, है ना, उन्होंने कॉमन कंट्रोल वॉल्यूम बता दिया और उसके लिए उन्होंने मोमेंटम बैलेंस कर दिया। ठीक है, सो दिस इज नॉट अ वेरी डिफिकल्ट डेरिवेशन, यू कैन इजीली अंडरस्टैंड इट। ठीक है, सो वी विल मीट ऑन द नेक्स्ट क्लास विल बी ऑन वेडनेसडे आई थिंक। ठीक है, तो वेडनेसडे को मिलते हैं। किसी को कुछ पूछना है? कुछ पूछना है तुम लोगों को? चलो ठीक है, फिर वेडनेसडे को मिलते हैं।
रिपोर्ट कर देना।
हाँ हाँ, इसको तो मैं कर दूंगा, इसको मैं भेज दूंगा आप लोगों को।